So let's get started. So just some admin thing first. Probably you know the homework 3 has been due last Friday. So I released the homework, which will be due next Friday, not this next. So you're given like more than 10 days to do it. So it will be homework 4. So it will be estimation and sampling distribution. So the topic 4 and 5. Okay. So the goal today is to we will cover the hypothesis testing, and this is going to be a rather long chapter. We expect to get it done in 2 weeks' time. So for 3 to 4 classes. Okay. So the main idea from hypothesis testing actually follow from or very closely related to the interval estimation we learned in the last topic. So that's why before I start, let us very briefly review what we have done in the interval estimation, an estimation part. Then we will see what were we doing. Okay. So just to remind you, what we have been doing was like the objective of what we actually doing in the second half of this course, or we're talking about there's a population we want to study, right? There's a business decision. We want to see what happened to the, say, consumers in the potential new market, right? Or existing market where there are many individuals here, right? Probably you want to ask how much money they want to spend on your product, or whether they like your product or not. Okay. And the thing we probably care is can be summarized by what we call population parameter. Mu and sigma square is the two things that probably you would care at the very beginning. You may care more, but these are the two things that you would care. And if you have every single individual's observations, then you can estimate this, right? And the problem is you don't, and we basically take something out, right? That is called sampling, right? And for this sample would be meaningful, we want this to be a representative one. Representative. And that how to get representative, the thing is we need a random sample. Okay. If random sample, that will be representative. Okay. And and how once we get this representative, right, that means that we want to use this small thing to look at the big thing, right? Just like look at the big picture from the small picture. And from that, we learn that 2 ways to measure those, right? We have X bar and S square, right? And of course, if the data is a binary data, then proportion pi, right? And in that case, that will be for that case is P, right? So that would be the 3-point estimator, right? To estimate them. Right, and we learned that there are beside this point estimator, right? This is a point estimator, right? We also have what we call interval estimator, right? Well, we learn interval estimator, and what we learn is it can be X bar minus M, right? And X bar plus M, right? Or you have P plus M and P minus M. And M depends on whether you know sigma or not, right? So if you know sigma square, right? M will be just Z alpha over 2 sigma over N, right? If you don't know sigma square, you don't know that, then M will be just T N minus 1 alpha over 2 S over root N, right? The idea is being a bell curve. I'm not going to repeat it, but I think that would be, you can check them back to be very clear, right? That would be like this. If you know this, there will be P1 minus P over root N, sorry. Okay. So that is what we have covered last time, okay? Last class, last week. So the main thing that we are interested in, right? Of course, there's something also what we call, this also imply the sample size, right? And if we fix the M, what is N, right? I M and I ask what's N, right? So what is the sample size that we need to see how we can understand this problem, right? So that would be the question, okay? And how this interval estimation relate to what we are doing today, okay? And that is similar to the idea when we talk about sample size, right? Determination is sample size estimation is fix M and we ask N, right? Ask how big the sample. Here now is related in the idea in the sense that hypothesis testing is we make some assumption, that's called hypothesis, right? We make some assumption about it, okay? Assumption, okay? Or what we call the hypothesis. And in some sense, this is very similar to the idea we learned from the Bayes rule in some sense. I mean, we didn't actually update, but somehow it's related to learning. Is the idea that we assume, okay, what are the meals, okay, for example, what is the population mean, okay? And in that case, right, we would see what we learned by law of large number, central limit theorem, or we're normality assumption that under what we assume, the sample mean will be will have the expectation at the population mean and looks like a bell curve, right? So this is what we learn, okay? So what we are trying to do is the following, right? We can assume this is true, and then we just do the sample, right? And suppose this is our data that found this out, and we can go left by M, right? And go right by M, okay? And if this interval, it doesn't include mu, okay? In that case, we would say the hypothesis is not supported by evidence. If yes, then the evidence is okay, it's consistent. At least we can't reject from the evidence we got. So there's a learning process, a particular way of learning, right? Is to see whether you do interval estimation, the interval actually include something we think at the beginning, right? If it is too different, too far away from what we found, they can't be the original claim is true, right? Suppose we hypothesize mu is like 5, right? For example, right? And your data turn out, okay, this is like 10, and the M is like maybe 2, okay? So your interval estimate is like 8 to 12, right? 8 to 12, that is not include 5, then you wouldn't believe that 5 would be something reasonable guess, right? If they tell you 5, then you figure, okay, I figure out that it's like 8 to 12, that cannot be 5, right? So that would be the idea. Okay, let me really repeat once again. So what we are doing, okay? So just to give a simple idea is interval estimator actually gives us the range of possible mu, right? Although before we do, we can say probability, but after we do is confidence. But the idea I'm saying is if our interval estimator, the interval doesn't include something we think that's right, then it's likely not to be right, right? We would say the data doesn't support what we are thinking, right? It's still possible, but it's so unlikely that you would think, and that is not possible. Okay, is that clear what we are heading? So basically, this is the main idea of the whole hypothesis testing, right? It's trying to see what we think is true, which is mu, and what actually has been found, right? What we're talking about is the distance between them, right? And how can we say that distance is large enough, right? You look at, in terms of bell graph, this area is very small. Okay, so that is the main goal of what we're doing. Okay, that later you will see this is what the purple area is called the p-value, but we'll talk about very soon. And that's the main idea. Okay, assuming what we hope for is true, and we see the data, is it far away from what we think? If two are far away, no, it can't be true. Is that okay? So that is the main thing that we are covering for this week and the next week. Of course, there's a different variation of how actually being done, but this is the main concept. I mean, this is the underlying idea, okay? And the technicalities lies on how you calculate this area, okay? Mainly how to calculate this area. Again, same as hypothesis testing, this area will use 10%, 5%, and 1% as usual benchmark, but that is the main thing we do. Is that okay? So I hope that I convince you, or at least convey the message that what we're actually doing for the rest 2 weeks is just different setting, how you do this kind of scenario. Okay, so I guess it's enough preview. Let's actually talk about things that we want to talk. Okay, so hypothesis testing. The formal idea of hypothesis testing is we want to see, here is a claim, okay, whether supported by a sample, actually by data, right? It's a data, try to see whether you want to prove is true or not. Okay, so probably before I go into details, so give you some application in your mind that you need to do, right? Something if many of you are actually from accounting, right? And you do audit, right? And you probably want to see if the client claim they have what you're auditing is they have so many inventory in their warehouse, right? That what you would do is to collect data and see whether what they claim is true, right? But when you do collecting sample, then there must be, you don't collect the full picture, right? You're doing sampling. So you want to test the claim whether it's true or not, right? Or like actual real practice, look at a product, how good is the product, right? Or how satisfied is your customer, right? So you ask enough people and see they like it or not, right? So that is something that you need to do, okay? So you'll be more clear, but that would be something that we often work on, okay? So the first thing we say is a null hypothesis, okay? Null, it's something that the claim we are making, okay? This is what we call, sometimes people call it working hypothesis. Okay, working hypothesis. And usually this is what we learn from the prior knowledge. Okay, This is coming from someone to tell you this, okay? Like suppose this is the smartphone, the iPhone. Apple claim it can last for like 13 hours, right? Then you want to see this is true or not. This is some the claim. Someone makes a claim. You want to test it, okay? And just like in the common law system, right? Like in Hong Kong or US, right? You are at the beginning, you would be assumed to be innocent, right? It's innocent until proven without reasonable doubt, then you would be guilty, right? So that would be the null hypothesis, okay? It's something that you would happy to keep if the evidence doesn't reject it, okay? There's something from history, power knowledge, or we give a benefit of doubt on this one, okay? So that is something, the null hypothesis. Now the next is what we call the alternative hypothesis, okay? That is something that we would like to accept it as the next null if the current null is gone, okay? This is something that we would be saying that this is the data. We are trying to see if the data supporting this alternative claim, okay? And usually its easiest case is null and alternative are complement, right? The null is guilty, the null is innocent, the alternative is guilty, right? That is the case in the court, right? But they need not be actually complement each other, okay? As the minimum requirement is they must be mutually exclusive, right? They need not be but usually the case is complement, but later you will see in the next slide or next two slides, the null hypothesis equally say maybe, usually we say mu is, the null is mu equal to say 5, okay? And the alternative can be, there are 3 ways later you will see, can be mu not equal to 5, okay? Which is exactly the complement, but it can also be 2 other possibility. Can be mu more than 5, okay? Or you can mu less than 5, okay? So 3 of them will be acceptable, okay? We will discuss which of the 3 is appropriate in which scenario, okay? But bear in mind that they must be mutually exclusive, but need not be complement to each other, okay? So the idea, as I said, you like the courtroom, you assume your null is correct, and you would reject the null if the data is very unlikely to support the null, okay? So that is the idea. I guess that should be no problem. Basically, just have the null and alternative. So this is the first line we're talking about. Null is what you're working on. Alternative is try to see if the null is reject, then alternative is something you take on your next null. Okay, that is something what we have. Okay, and the other application you can imagine is like you are a consumer counsel. You want to take a look at the food product, right? Whether the active ingredient, right, is more than, no less than what they claim, right? Say someone claim a medicine, right? Then they must have the active ingredient have this much, right? But anyway, we'll give more example. Okay. So besides we say null alternative, there are 2 ways or 2 types of hypothesis. Okay, one is called simple. Okay, the other is called composite. Okay, and simple means we assume talking about a particular value, so like equal to is simple. Okay, and here is interval. Okay, interval is within some region, okay? This region need not be continuous, right? Because mu not equal to 3, okay, is also composite, right? Because it's like, this is, what does that mean? It means the following, right? It's mu less than 3 or mu more than 3, right? So it's within some interval, right? Still less than 3, more than 3, okay? So for our class, okay, or actually in most practice, okay, what we have is null is simple one, alternative is composite, okay? And you probably ask why we have that, why we don't have a composite null and simple alternative. That sometimes is possible, okay, but if you try to look at textbook, they are really complicated. So we focus on the simplest case. We just focus on simple null and composite alternative, and that actually cover most application we think in our real world one. So for business application, you don't really need to worry. So this is the sufficient for our purpose. Okay. So if you want to know more, that is way beyond the scope. Okay. So even I don't think anyone in undergrad will learn beyond that. So no matter, I think even you go to stat department, unless you go to very advanced class, and I think this is something that they will work on. Okay. So that is not a big restriction, even though you go to stat department. So it's not hugely restrictive. Okay. The next thing is about one-sided, two-sided. Actually, we hinted already. Okay. And as I said, one-sided means, say, mu equal to, mu less than 3 or mu bigger than 3. That is called one-sided. One-sided actually means you can see is the whether you consider something as a evidence that go against your null, right? And you probably ask what to use, when to use which, at what scenario, right? It's depend on application. Okay, usually, at later few slides would say, it's depend on when bad thing happen. Okay, if you are a producer of medicine, right, where the exact ingredient is crucial, which means that if more than or less than is a big mistake, then you have to use the two-sided one. Right? You cannot be more, just like accountant, okay? Look at the inventory, less than or equal than would have a serious consequence, right? Because less than, maybe there's some big problem, more than also the problem, right? It's something that you would be serious concern. And when you would use less than or more than, right? If you are a producing food or candy or what, okay? And the toxic ingredient, okay, or some additive, then in that case, more than you would go to jail, right? Less than is fine, right? Your toxicity or your preservative or anything that is more than will be a big issue, right? If you have less than, you don't have a problem. Okay. And similarly for less than, again, assume your food company, right? Maybe you are selling chocolate, right? And you claim that the chocolate has 80% of chocolate, right? Of course, 20% more can be other thing, right? And you actually have 81, actually no one will complain, right? More than what you have is fine. You claim at least 80% is thing, then you have less than, then probably consumer will not be happy, right? So it depends on application which one to choose. Okay. Of course, if you don't know which one, then it's two-sided, right? That's a very natural way, right? But if you know the consequences is only in one-sided, then you do one-sided, right? Or you actually know from theory, okay, it must be one side or not, then it's very clear, right? It's a one-sided, right? Or from the definition of the variable, it can be just one-sided, right? Say, how much money people spend on, I don't know, nonsense stuff, okay? Maybe buying emoji, I don't know, whatever something you think is not worth spending money, and you want to see whether people want to spend money on that, right? And the spending must be positive, right? You want to check how many people spend on that, right? Maybe something like how many people is spending money on alcohol or cigarette, right? Or this other bad thing. And in that case, the money spent is at most minimum zero, right? You want to test is spending more than spend a lot real mean more than zero, then you have to look at more than zero, right? There's one-sided, not two-sided. Okay, so that would be the thing. But for a purpose, later you will see is like focus on the bell-shaped thing. So you don't have this real result on data. Okay, and for a purpose, you just need to worry about whether one-sided has bad consequence. Okay, for your application. And as I said, generically, you focus on the K two-sided. Okay, that would be the, unless you talk about what we have said, it's very clear by law. You have be less than or more than. In that case, you would be focused on one or the other two. Okay. Now, once we have that, as I said, there's a two-sided, right? Is you don't know which way it should be, right? You don't have good knowledge about, or the accuracy is important. Okay, I think I have mentioned already, right? And the one-sided is you know which sign is more important, right? The say quality control, right? In that case, harmful substance will be more than, and main ingredients will be less than as alternative. Is that clear? Is it okay for this few slides? I've already discussed it, so I just so here is a few terminology that you need to know, because it is often used in reading statistical report. They usually assume you know this terminology, okay? And there are what we call type 1 error, type 2 error, which is actually often use it without describing, so you have to know what they are. So type 1 error is the error that you actually reject the null, even though it's true, okay? So this is due to probably it's like the sampling mistake. Okay, consider the case where we have the sample mean, remember, okay? The sample mean, okay? And this is the mu, okay? And assume central limit theorem applies, right? This is a bell curve, okay? And the bell curve indeed imply X bar can be very small number, can be very big number. It can be very, very big, can be very, very, very small. And no matter later how you do things, it can easily got rejected, because like you may end up in a very, very small number, right? And you later, if you try to draw interval, right, you may exclude mu. Okay, so that is the error. Okay, and the notation is called alpha. Okay, this alpha indeed is the level we are willing to accept. This is something directly chosen by us. Okay, we choose this alpha. Reason is because this X bar is here, right? We are going to choose what is the distance I would think that's large enough, right? And in terms of the probability, that means that I want this area. How large is this area? I would be willing to say it is small, right? And later you will see this is with alpha, okay? Depends on one side or two-sided, okay? But this is a number that closely related to alpha, okay? Depends on. But that is the main thing, okay? Is alpha is something we decide, okay? It's our level that we accept it, because this case is normal, right? The bell curve can go from negative infinity to positive infinity, right? There is no way to make this alpha go to zero, right? We must have to have some number there, right? So it must either, as I said, alpha is like 0.9, sorry, alpha is a 1%, right? Or 5% or 1%, right? So these are the these are three choices usually you would do in practice, right? This is the level of error you're willing to accept, right? So the smaller alpha, the more careful you want your conclusion to be, right? Say that is the level of reasonable doubt that you would willing to make, okay? The smaller the alpha, the more difficult to reject, okay? You're doing more careful decision, okay? The next one is again closer to alpha, okay? It's what we call the you make the wrong decision, you reject, okay? You fail to reject the null, okay? What we assume is wrong, but you can't do it. Just like the guy is guilty, but you set the bar so high that you cannot prosecute, right? You can't, you know that guy is guilty, but yeah, but you just let it go, okay? That's possible, right? Because the guilty criminal may actually we've been very careful, or you are lucky, the evidence is erased by the environment, the rain, the tornado, whatever, earthquake, whatever, or lucky there's no one around, and then he or she just escaped from the justice, okay? And that is the number we call beta, okay? And as in general, okay, we choose alpha, and in the next slide also we said alpha and beta are trade-off, okay? So if you choose a small alpha, the beta will be, okay? We don't prove this point, but that actually can be done by telling you that alpha and beta are trade-off, okay? Larger the alpha, smaller the beta, okay? And and of course there are many. This is the how strong the prosecutor you are using in some sense, right? It's how strict the prosecutor is using, and that's why when you look at they would call this beta is the power for the test, okay? Power, and there are many procedures to do this hypothesis testing, and some things have higher power, some have lower power, okay? So it depends on the problem, but people can say the power, then it's like 1 minus beta. It's like whether it's able to reject the right thing, okay? If false, I can't reject it, right? So if high power is how smart the prosecutor is, right, in terms of the courtroom analog, okay? So I mean, I do understand there are many terminology here, but that is the usual terminology you will see when you read this or you read any statistics article. So I really can't skip because they just use it without defining, right? So I have to tell you this. And also that actually connect to what we have learned. Alpha is called confidence. That is what we learned in the previous chapter topic. And they also refer to this alpha as called the significance level, okay? And this significance level is important because we will use it terminology for the rest of our class for this topic, okay? We keep talking about significance level. Okay, we say 5% significance level, 10% or 1%. So this is the terminology we're using. Okay, and beta we don't mention in our class after this slide or the next slide because implicitly when you take alpha, beta is already determined. Okay, so oh sorry, so I should say if you have yeah, let's see the next slide. Okay. So here is the usual graph you will see is there are 4 situations when you make decision based on data. Is there are 2 kind of scenario, right? Is now is true, now is false. We never know which one. We don't never know, and you have to make the decision. Okay, if you choose the alpha, okay, that is correct with 1 minus alpha, and you reject with 1 minus alpha. Okay, you choose the alpha, remember. And if wrong, this is the beta. Okay, 1 minus beta is you get it right, beta get it wrong. Okay, and here is the alpha and beta is a trade-off, right? Or the 2 error. If you make one larger, the other one have to be smaller, right? You make one smaller, the other one larger. Okay, and the question probably you want to ask is how to make both smaller, right? Because this is the goal, right? Make the error smaller, right? The only thing you can do is to make a larger sample. Okay, the larger the n, okay, both will be reduced. Okay, that would be an easy thing. As I said, there's a rule of thumb for alpha. Okay, so that would be the terminology we have been learning. Is that okay? Any question? I know I'm obviously know that there's a lot of new terms, but it will take you some time to familiarize with those terms because you have to relearn this term because they just use it. Okay, we just have to follow what have been doing in the study. Okay. Any question? If no, then we go to directly go to the procedure. Okay, and these 3 steps are the procedure, the standard for the rest of the course. Okay, so rest of this topic. So we'll be doing at least more than 10 to 12 different type of procedure, and they all follow the same. Okay. So the first thing is we'll give example, but just the abstract way is you need to tell me what's H now and what's H1, and either you'll be given by your boss or you have to infer that, right? But usually in our class it's like mu equal to some number, and alternative is either mu not equal to 5, mu less than 5, or mu greater than 5, depends on as I said, depends on what scenario you're working on, right? So we just write down that you infer from the question, and and we will make assumption on data, right? Say suppose normality, right? In that case, we will having this X bar is following a bell shape, right? Mu is here, right? And the variance is maybe mu is making smaller here. Right, it's the C mu, right? And this is sigma square over root n, or n, right, is the variance. Okay. So the main idea here is we know this distribution, right? And under the null, this is what happening, right? This will be 5, will be there, right? We know this number. And based on sampling outcome, okay, is suppose it's like here. Okay. The question is X bar far away from mu? Okay. Is X bar far away from mu? Okay. So if say it depends on if this violate this, okay, the question depend on the answer depend on which one you're using. Okay, depend on what is the alternative. First, easiest thing is if this guy, suppose we have number one, we have mu less than 5. Okay, is it going to be evidence against or what we want, right? Is it going to be the evidence we're going to accept? No, right? If our alternative is mu less than 5, right? Then what we get, remember this is 5, right? Yes, oh no. If we get x bar is 6, right? So that is not going to be helping our alternative, right? Just like you are trying to claim the defendant, right, is guilty of a murder, but that guy is actually have alibi, which he stayed at home sleeping. Okay, and there's no sign he's going out, and there's no way he committed the murder in, say, in somewhere far away, right? In that case, you don't need to do anything indeed, right? And in this case, right, number 2 case is mu bigger than 5, right? In that case, you would be looking at, okay, is it far away enough, right? And if far away enough, you're looking about this area, as we mentioned, right? Is this area small or big enough, right? And the criteria is looking at this is how big and how small is this guy, okay? And usually we would, instead of working on this, okay, this is standard thing we work on instead of the x bar, we're on the z, okay? So this is 0, okay? Okay, we will convert this, I don't know, this number, okay, suppose this is 7, okay, I don't know, or some number there. We'll convert this to here, right? Will be x bar minus mu, which is 5 over sigma over root n, okay? We calculate this. This is called test statistic, okay? This is statistic, we're actually going to do the test, okay? And we're looking at this area, it is small, okay? Is this small enough, okay? We compare this area to our alpha, okay? This area under the case 2, this is called the p-value, okay? This p-value. If this value is way less than alpha, we decide earlier, say it's less than 5%, less than 10%, or less than 1%, which we decide at the beginning, usually 5%. Then in that case, we would say we would rather don't reject the null, and we will say we are going to take the alternative, right? That they would prefer the alternative, okay? So that would be one way to do it is compare the p-value and the alpha, asking whether p-value is less than alpha or less than or more than alpha, right? If less than, you reject, right? Because it is so unlikely that coming from what you propose, okay? You propose mu is say 5. If it goes 7 is so far away, the yellow area is so small, smaller than alpha, then reject, okay? And this is one way. The other way around is to look at what we call the critical value, okay? Critical value is very similar idea, okay? Instead, it's asking the following, okay? It's asking if asking the z alpha, okay? So what's asking is we have 0 here, we have alpha here, this is z alpha, okay? We're asking, is the z alpha less than x bar or more than x bar, right? if Z asking this is the Z here, right? Compare Z is more than or less than, right? If Z is more than Z bar, sorry, if Z is more than Z alpha, then you reject. Okay, if Z is less than, you will not. Okay, we'll give you detail more about it, don't worry. But this is the main idea behind what we are doing. Okay, so don't worry, we will operationalize this after the break. Okay, in the meantime, we have a break. We'll resume at 1:30, and then we'll go through examples, right? We go through each case. I only talk about the one side alternative. Two sides more complicated, but we will do the one side first and then do the two side. Okay, we just do one by one, step by step example. So don't worry, you will be immediately. Okay, this is just overview what we're doing. Just at least we have some idea what we're heading for. And after this class and next class, I'm pretty sure you know, because we're just repeating this unfortunately, we're repeating this many times in different scenario. It can be very boring, okay? But but we need to tell you different scenario, different situation, how we apply those. So, but bear in mind, this is actually what we'll be keep doing this under like 10 different scenario, okay? So this is the main idea. So there's a 3-step, just bear in mind. So let's have a break of 10 minutes. I will go around to see if any question, okay? Okay. Okay, so let's get back. As I can see, many of you might still be a little bit uneasy about the high level about what we're doing. So let's go exactly to how we actually implement this in various example, then you would be very comfortable. So don't worry, they are very straightforward. Okay. So let me start. So we will focus on sample mean, the test until except the very last one. Okay, we focus on sample mean except the very last test in our course. Okay, so we will for the class assume normality. Okay, so which means that the bell curve is always true. Okay, for our population. Okay, so that means that this is something that we will have in our mind. Okay, so the only thing that you need to worry is whether we know sigma square or not. Okay, and as you would be thinking from the last topic, whether you know this will decide whether this is a Z or a T, right? Because you don't know this guy minus mu over S over root n is actually T n minus 1, right? So that is the comparison, right? Because if you know, we'll be using this one, right? This is normal CO1, right? That is the Z. So that would be the thing we have been doing, okay? So we'll focus on the first one, okay? today. If we have time, we cover the second one. But I guess we only have the time for the first one. Okay. We'll talk about the t-test in the next class. We focus on Z1. Okay, the Z-test. We assume sigma is known. Okay. So that means that we have some idea about sigma square. Okay. And there are some way to estimate those, but we don't talk about this in this class, so there'll be some way to estimate. Okay. Let's actually look at this, the purple one. Okay. So the rule is the following. Okay. So what we are going to do is, this is our null hypothesis. Okay. And we know this would happen. Okay. So just this, and A is here. Okay. And what actually we are doing is look at the data. Okay. We try to figure out data. Okay. The data may be here. Okay. This is your data. And you try to see if this is close enough, right? And what you're going to do is transform it to Z, right? This is 0. You would be trying to, this guy will be x bar minus A over sigma over root n. Okay. So that would be the goal. And then we will check this area. Okay. Is it big or small? Okay. So that would be the goal of what we are doing. Okay. So so we will be looking at 3 different types of H1. Okay. So focus on the case is more than. Okay. So that's what I said is you have Z here. Okay. You will try to see if this is x bar minus A over sigma root n, right? There are 2 ways to do this. One is to look at this area, because we just on the right hand side. So this is the area. Okay. If this area is it less than alpha? If less than alpha, then you reject. All right, because less than alpha, which means that this distance is very large. Okay. That means that what we claim is cannot be supported by data. Okay. If this is bigger than alpha, then you have no problem, right? So obviously, if your data is on the left-hand side of 0, then you actually don't need to do anything, right? Because on the left-hand side, this must be bigger than 0.5. So our alpha is like 10%, 5%, or 1%, so you never reject. So this is what we claim is the p-value idea. Okay. Look at your data, look at the area compared to alpha. Okay. So that would be our first way to do it. Okay. And we also said there a second way. Okay. First, we can compare this area to the alpha, right? Or you can look at the other way around. Look at the other way around. Not look at the area. Okay, so this is still x bar minus A over root sigma over root n. So what we're going to do is compare this to, say, Z alpha. Okay, if this Z alpha is on the left-hand side of what we're doing, okay, that means that this, by definition, right, this area is less than alpha, right? So we're done. Okay, so either you compare the area, or what we call compare the critical value. This is called critical value. Okay, Z alpha. Okay, so these are the 2 ways that you would work on. 1 or 2 ways. Is that clear? I mean, you'll be really clear because we'll be doing the example. But there's either you compare the area, you compare the critical value. Okay. I mean, still we're abstract. I would say so. Let's go to example, and quickly then you will see how we operationalize this. Okay. This is just describing the detail. But if you don't, I don't think we need to talk about this because you will easily see what's going on. Okay. So let's see the example very carefully. If you don't follow, then I will be slowing down because this is the first crucial example that you try to understand, okay? So we start with a population, with a normal, right? This is very important, normality, and standard deviation of 4, okay? So this means that we start with this assumption here, okay? We know sigma square over n is here, depend on the sample size, okay? So this is the normal thing here, okay? And we know sigma is 4, so let's write down here as well, okay? So this is the information we have in the first sentence. The second sentence we said is we have a sample of size n equals 64, okay? And we have mean x by 7, okay? So look at the things we want to check, okay? The things that we want to do is we assume mu is 6 and alternative mu bigger than 6, okay? So which means under this, assume this is true, this should be 6. Okay, so this is the assumption coming from the null hypothesis. This is a working assumption. So what we have the data is 7 here. Okay, so that is what we have. And remember the null is more than, okay, the null is more than, okay. So at the beginning you can check at least in paper on a surface 7 is kind of related to more than 6, right? If your data is 5, then probably you can just go home, right? Because the data doesn't actually is done, right? So you don't need to do further, so it's done, right? But now it's 6, so okay. Let's try to analyze how is 6 and 7 is sufficiently big enough, right? It says 7 is the distance between 6 and 7 is large enough to say x0 is x now is wrong. Okay, it's not supported by data. Okay, the easiest thing in what we do is we do a 5%, alpha is 5%. So we just try to see if this is less than 5%. Okay, if this is less than 5%, yeah, then we say we are not happy with mu of 6. So that's the idea. Is that clear? I stop here a little bit. I mean, make sure that you understand the setup. Is that okay? So let me repeat what we are doing, okay? So we have the data. We know the sigma is 4. Don't ask me how we know. We will talk about t-test, which we don't know in general case, but sometimes you know some way to estimate this 4, okay? And it's okay to overestimate 4, so that's fine, okay? And there's many ways to overestimate sigma, okay? For example, range is always bigger than standard deviation, okay? But anyway, that would be something beyond what we are covering, okay? So suppose we have some estimate on this one, okay? And what we do is we have a sample size of 64 and mean is 7, okay? And what we are working on, the problem is more equal to 6 or more than 6, okay? And at least on the paper, 7 is more than 6, so that is we need to check whether it's big enough or not, okay? The criteria is the area. The blue area is it less than 5%? Okay. If it's less than 5%, then we will say it's far away 5 and 6. Then we will say 6 is wrong. Or we reject the H null. Is that clear what we are doing? Is that okay? Is that clear in principle what we are doing? Okay. And and as usual, okay, we will actually not calculate this guy, although now you can actually do it. I mean, because of the computer, you can actually calculate this guy, okay? But in general, we don't actually calculate on the Z, sorry, and X. We would transform this to the Z one, okay? And you ask why we do this, because we actually need to do it when we talk about t-test, okay? So let's try to be consistent. So we transform it to Z, okay? And the 6 will become 0, okay? And we have a t here. That's that here, right? And the question is, this guy, right? 7. What's this guy? Okay. This guy, how we get it, right? This guy, when transform, is actually x bar minus 6, right? Actually, we can put 7, right? 7 minus 6, actually it's here. So maybe I might just as well put it here because I don't need to write this one. It's 7 minus 6, right? Because it's x bar minus a, which is what you propose to be, over sigma over root n. Okay. So this turned out to be 2. Is that okay for this one? Okay. This is how you transform, right? Because we learn under this, right? X bar is a normal distribution with mean 6, 4 squared over 64, right? So this is what you learn from the normal assumption, right? The normality assumption, right? This is what you learn because the population is normal, okay? And the sample mean is also normal, right? This is actually what you learn from last 2 weeks. Is that okay? Then that's why you can transform this, right? You minus 6 over the square root of the variance. Okay? Because this is the sigma over root n, right? Just 4 over 64. Okay. So now as we see here, which we found to find this guy, right? This area. Okay. That is the p-value. Okay. How can we find this p-value? Okay, this area. We can find the complement area. Maybe I use what color I should use? Purple? Yeah, purple. So we can find this area. Why? This area is just norm, right, as this to true. And maybe I write again because just go into the other side. It's the norm as this to true. Okay. And the red will be 1 minus this guy, right? Because the area left and right add up to 1. Is that clear? Because Excel always keeps the error to the left. Okay, you just have to subtract it from 1 because left and right is equal to 1. Is that clear? Okay, so let's actually do it in Excel. Okay, let me do it in Excel. Okay, just look at the bottom, right? Maybe I just do it here. Okay, we want the norm as this to true. Okay, do remember this is going to be the purple area. Okay, so you need to subtract it from above. Okay, so that gives us what we want. Okay, of course, if you're quick enough, you can do one step and that's it. Okay, you can do this. Okay, so that is either you do the first way or the second way. Okay, either you do the maybe same as what you're doing. This is the purple color. Okay, it's okay. I think it's okay. It's clear what we're doing. Is that okay? How we get this p-value? And this p-value, the blue area, is less than 5%, right? It's less than 5%. So we would be saying that we will reject mu equal to 6. Okay, so that means that 6 and 7 is large enough to say that mu is 6 is wrong. Okay, we are rejecting H now at 5% significant level. This is what usually you see people how you write is we say reject this at 5%. Okay, Is that clear what we are doing? Okay. So this one way you call p-value. Okay. And this is the way you done, but usually there's another way to look at it, right? Instead of looking at the value on area, you actually want to see if 2 is too big or too small, right? And what you're trying to compare is the following, right? What you are doing in the other way around is what we call critical value method, right? It's the following. Instead of looking at the area directly, okay, what you're doing is look at this graph, okay? This is the 2 as usual, okay? We are trying to show you the following. Maybe other color, green color, okay? We want to look at if that's alpha, that is Z alpha, okay? Alpha is 5%, okay? And we don't look at this green alpha, okay? If this Z alpha is on the left-hand side of 2, right? And then you reject, right? Because on the left-hand side means that the area on the right of 2, right, is less than 5%, right? Is that clear? Is that clear what we are doing? Okay. So how to find this Z alpha? Okay. You want from the area go back to below. That is how you can do that. Is very simple, right? Do remember Excel always do the left-hand side. Okay. So if the right-hand side is 5%, the left-hand side is 95%. So what you have is just norm S inverse 0.95. Okay. Then this gives you 1.64. So that is how you. Then 1.64 is the 2 is larger than 1.64, so you reject. Okay. So this is what we call the critical value method. And you can easily see that they're the same thing, right? Just look at either you want to move the 5% to the Z value, or you move the Z value to the area. Okay. So either way, it's the same thing, right? Either you move to your target or you move the target to you. Same thing, right? So the same thing here, right? And let me do this norm S inverse 0.95. Okay. Norm S inverse 0.95. Okay. So this is 1.64. Okay. And you can do it, as I said, you can do it as that table, give you the same thing. Is that clear? Is that clear how you get this? I mean, in the meantime, I just stop here for 30 seconds before I talk about the other one. Okay. We'll do the left-hand side again. Okay. So now we'll do the right tail test. We'll do a left tail. Okay. So before I go, I just give you 30 seconds before I proceed. Let me know if any question. Is that okay? Is that okay? Okay. So don't worry, we are doing another example, but on the left-hand side. Okay. So then you will see how we work on this problem. Okay. So we're the same, but you have to flip your head left and right. Okay. So this is the idea. And now we are rejecting on the left-hand side. So just this is A. Okay. So if X bar is too small compared to A, then you reject. Okay, exactly the same idea. Okay, so let me actually do it because I think all the math is the same. So just let you see the logic. Okay. So again, let's look at what we have in the question. Okay. Again, with the same idea with normal, with sigma is 4, and then we have N64. And now the only difference is they still have X bar with 5. The only difference is this guy and this guy is different, right? This is only different from the previous example. Okay. So what do we have here is under normality. This is what we know. We have X bar. Okay. And under this, okay, we know if this is true, this must be the case. The bell is here. Okay. Sigma square over root n here. So sigma square over n. Okay. And sigma is 4. Okay. N is 64. Okay. And what we found from the data, let's highlight in the blue color. Okay. This guy means 5 is here. Okay. So the question is, we try to see is if 5 is very small compared to 6. Okay. Again, the question is if this area is small enough. Okay. If this area is less than 5% or 1% or 10% as you like, then you would say they are far away enough, then you reject mu is 6. Is that clear what we're doing? Okay. So we will have the procedure. Instead of looking at this directly, we transform this to the Z environment. Okay. But we're looking at Z is here. Okay. We'll go down. This is 0. Okay. Okay. And how you make 5 to down here is -2. How so? Look at this here. Okay. You would subtract it from the mean, right? And over sigma over root n, right? Because this is sigma, this is n, right? Sigma is 4, n is 64. So it's -2. Okay. So again, it's very simple. Look at this area. If this area less than 5% or not, less than 5%, bye-bye, right? Not bye-bye this class, let's bye-bye the hypothesis, right? So how you can do this? Excel is very simple, right? Already it always gives you the left area, right? So exactly this one is simply what? Just simply norm as this, right? -2 true. Okay, and that's it. No need to 1 minus because this is already the left-hand side. Okay, and this is going to be, we have found it already, it's going to be this guy. Okay, and this is less than 5%, so we reject. Right? Is that clear? Maybe I can go to Excel again if you need to. Is that clear? How we are doing it? Okay. So let's go to Excel. I just do it once more. But I hope at this point, I mean, some of you actually worry about Excel. I hope that is already very clear what we are doing. Okay. It's always the left-hand side. Okay. It's going to be 2%. Okay. And 2% would mean that we will reject. Is that clear? Okay. And I would like to point out how you can do it in the critical value method. Okay. We will look at, instead looking at this number. Okay. other color. Okay. What we're actually doing is this, Z. This is 0. It's a bell curve here, okay? And here we have -2, okay? So what we want to show is indeed the critical value, okay, which is given by, this is alpha. So this value is -Z alpha, okay? So I want the 5% on the left-hand side, right? And this value is actually use the Excel, it's just the norm S inward for 0.95, right? Maybe I clear the blue one, right? It's just, sorry, it's 5%, sorry. 0.05. Okay, because this is just the left-hand side is 5%, right? So this will give you -1.64. Okay, so let's see the number again. We have norm S inverse 0.05. Okay, so this is exactly -1.4485. Okay, so the -2 is way more extreme, the critical value, okay, then you reject. Okay, is that clear? Either the p-value is very small, or the value you calculate, the t-statistics is -2, is way more extreme than the critical value. Okay, either you more than critical value, or your p-value is less than alpha. Two ways you would prove it. Is that okay? Is that clear what we are doing? Is that okay? So either way would do what we want. Okay. So usually you would do one way sufficient. You don't need to do two ways. Okay, do the same thing. Is it okay? If okay, then I will talk about the very last one. Is that okay? So we talk about here. Talk about the two-sided test. Please pay attention because this one is a little bit different. Okay. So the main idea is the same, right? We have X bar here. Okay. That's A is here. Okay. But the idea is that you don't know the data can be left or right. Right? That means that you have to make same as what we talked about. This is 1 minus alpha. You have to put alpha over 2 on both sides. Okay? So basically later you transform it to the Z. Okay? You will be looking at these two areas. Okay? Each is alpha over 2. Okay? This is the only difference. The first difference. Okay? The second difference is in terms of p-value. Okay? Because you don't know where you should go. Okay? So suppose you end up in here, okay, which is here. Then this is your area. Okay? This area is not the p-value by definition. You have to multiply by 2 and compare alpha. Why? Because you compare this area with alpha over 2. Right? Then to make it simple, you can compare this 2 times the area to alpha. Let me repeat it. Okay? You should actually compare this area to alpha over 2. Right? This area and alpha over 2. Right? But by usual way, we just compare 2 times the area more than or less than alpha 2. So the same thing. Okay. So that's why the p-value has to multiply by 2. Okay. So that is the main difference between the two sides and one side. Okay. The p-value you found has to times 2 because you compare alpha directly. Okay. Of course, you compare alpha 2, you don't have to do it, but by convention, you multiply by 2. Okay. So that's only difference that, I mean, the same, you can see the same logic. We will do it again, so don't worry, but that is the main idea of p-value. You multiply by 2 and compare. The reason is before you do the exercise, you don't know whether it's left or right. Okay. You tell us left or right, you don't really know, but if it's left, then you have compare over 2. Okay. Now let's go to this example we work on. Okay. So this is exactly very similar to what we have done. Okay. So let's quickly. Okay. And the question is the same. So we have X bar here. Okay. And again, there's a normal. Okay. So that's why our null is 6 here. Okay. This is null is 6 here. 6 here. Okay. And again, we have the same. Now we have X bar is 5. Okay. Turn out to be this guy is 5 here. Okay. Now, what we want to look at is this is far away. We'll look at whether this area, okay, is smaller or less than alpha over 2, right? Or 2 times this area is greater than alpha or less than alpha. Okay, so that is the main thing we're looking at. Okay, the same thing, but because of you don't know left or right, so have to be alpha, have to separate the two parts because it can be 7, it can be 8, it can be 4, right? You don't know which side, so you have to you assign alpha on both sides, right? Because alpha is, even if it's true, you will reject it, so it can be both sides. But alpha is the type 1 error, right? Even this is true, I mean, it still can be there, right? So what we are doing is very simple. We just transform this to Z, right? Z is here, and this is 0, right? You also draw this guy again, okay? And here's the blue thing, okay? The blue thing. What's blue thing is exactly what we have done, right? You subtract 6, right? And this is sigma, this is n, right? This -2 is here, okay? And again, what we are asking is this area, we want to times 2 and compare to alpha, okay? Let me repeat it, is you look at this area, you times 2 compared to alpha, right? Or this area compared to alpha 2, right? But you just multiply by 2. So this area, probably you would see how do you calculate this guy, right? This area is just the norm as this -2 true, okay? This is this area, but if you want to calculate p-value, you need to multiply by 2, okay? This gives you the p-value, okay? The norm, this is this area. You times 2, you compare to the p-value. Is that okay? Because this is how you calculate p-value, okay? Do I need to show you how to do it again? This is the p-value, is p2 times norm as this -2 true, okay? And the p-value is going to be 0.04, okay? So that means that if you use 5%, then you reject, right? If you use 1%, you don't reject, right? So you have 1% don't reject, right? 5% reject, 10% you reject, right? Is that clear? Because 1% is not small enough, right? But use 5%, you still reject. Is that okay? And finally, before we end, we can do the critical value method, right? You just look at the following, right? You just look at the critical value method. Is look at this. the Z, this is 0 here, okay? And do look at here, we look at this is alpha over 2, this is alpha over 2, okay? Same as interval estimate, right? Common interval. And we look at these two numbers are Z alpha over 2. This is negative Z alpha 2. Okay? So how to find this guy? Okay? This is 5%, right? Alpha is 5%, right? So this is the, if this guy is just the norm S inward, okay? 5%, so divided by 2 is 1 minus alpha is 0.95. Sorry, let me do this. Alpha over 2 is 0.025, okay? So 1 minus alpha 2 is 0.975, okay? So this is 0.975. Is that okay? Now, because this, the other way around is look at this is 95%, okay? So both side left is 12.5%, okay? So we just input this number, then we are done, okay? So I just show you the last operation is the norm S dot inverse, okay? 0.975, okay? Is 1.96, okay? So, and what we have is the blue one, okay, is -2, okay? And these two guys is 1.96 and -1.96, okay? That means that your blue area is more extreme than the critical value, then you reject, okay? Either your p-value is much less than alpha, or your test statistic -2 is more extreme than critical value. Okay, so I will see you see you on Wednesday. Okay, and we'll continue to do this, but in terms of the T test. Okay, have a nice day.